my name's Chris Harris and I'm from Allery Chemistry, and welcome to this video on OCR aromatic compounds. So the whole point of this video is to go through this topic, this video is specifically designed for OCR specification. So if you're studying that at A level and you're studying this particular exam board, then all the information in here is relevant to you. And there's no more information that you don't need to know. So it's designed to review the content that you may have already learned already, or you may not be at school or college and may be learning it from home. In which case this may be fairly new content to you. So however you're using it, it's appropriate for that use. All the videos is a full range of videos for all OCR. Year 1 and year 2 and all other major exam boards as well that are specifically designed for these each of their specifications, so they're tailored to that. They're all completely free to use, but all I ask is you please subscribe to the channel to show your support, and if you click on the subscribe button either at the bottom of the video, or you can see there's cards at the end as well where you can click on it and subscribe, or even just go onto the channel as normal. So yeah, they're all for free there. But if you want your own private copy of these slides here, they are available to purchase. If you just click on the link in the description box, then you'll be able to get access to them. But the video is obviously completely free and all available on Allery Chemistry. So this video is designed to go through the content. Like I say, it is important to actually go through exam technique as well, because it's one thing knowing the content, it's another thing actually putting it into place and putting it and answering an exam question. Exam technique is just as important, so please practice your exam technique. And I have done some videos, and if you have a look on Allery Chemistry, where I've gone through some past paper questions that go through that, so you can see for yourself on there as well. Okay, so let's make a start. So like I say, this is dedicated to the OCR specification, and so it goes through content such as benzene, electrophilic substitution. So these are the reactions that happen with benzene and phenols. So it's all aromatics. So it's already starting to smell nice already. Right, so let's look at benzene first. So a lot of the topics are going to be on benzene, of course, so we better see what it's about, shall we? So benzene is cyclic. It's a planar molecule, so it's flat, and it has a formula of C6H6. So carbon normally has 4 valent electrons, and each of them carbons is bonded to 2 other carbons in a benzene ring. And you can see on here, you've got the carbons, which are the purple atoms, and you've got the bonds here, which each carbon is bonded twice. The final lone electron, so you've got one hydrogen atom as well, which is here, and the final lone electron then orbits its way around one of these spare orbitals that exist on the carbon atom. Okay, so that sits above and below the planar ring. So you can see it's planar, apart from the orbitals which stick out. Now what these lone electrons do is they actually combine to form a delocalized ring, and you can see here it looks like a donut. So you've got a delocalized ring system here on the left hand side, and so that delocalization actually gives benzene its unique characters, which we'll look at in a minute. So all the CC bonds in benzene are actually the same length, and they all have the same bond length of 139 picometers. So you can see here that obviously a single bond would be longer than a double bond, because you might have double bonds here normally, single, double, and we'll look at that model in a moment and prove why that's not the case. But normally bond lengths are different, but in benzene it's very strange that it actually has the same bond length. So this is what I was saying. So with the single and double bonds, the CC bond length in benzene is normally between 154 picometers for a single bond and 134 picometers of a double bond. So actually, it's not a single bond and it's not a double bond. So it has like a unique feature, this benzene. Okay, so benzene's normally drawn in the skeletal formula just because it's a lot easier to draw. There's a lot of atoms in a benzene molecule, so it's easier to draw as a skeletal formula. So this structure here shows benzene with double bonds, and it's also known as a Kekulé structure. It was named after Auguste Kekulé, who discovered it. And basically, he thought there was alternating double and single bonds, and you may see it like this, where you have alternating single and double bonds, or you can see it like this, where you've got the delocalized system being drawn. So we just draw a circle in the middle. Now, at A level, you'll more likely see it drawn as the one on the right here, which is the one with the delocalized system, rather than Kekule structure. Although sometimes it's easier to draw reaction mechanisms using Kekule structure, but at A level you're mainly going to see as the circle. So that's what I would suggest you draw it as, rather than Kekule structure. So remember, even though we're drawing the skeletal structure, it's sometimes difficult to spot what atoms are actually in there. But remember, because it's a skeletal structure, hydrogens are not shown in that diagram, but there are hydrogens attached to each carbon. So each point on this hexagon here has a hydrogen hanging off it as well, but we don't show them obviously in skeletal formula. Okay, so let's look at the stability of benzene. So actually benzene's more stable than the theoretical cyclohexane 1,3,5 triene. That's the one with the 3 alternating double bonds. And actually scientists have looked at scientific evidence, and that could be through chemical reactions, X-ray crystallography, etc. So what they've done is they've actually looked and thought, well, actually it's more stable than we think, and it doesn't have this 1,3,5 triene structure or the stability of that. So we measure the stability of benzene by comparing the enthalpy change of hydrogenation in benzene and cyclohexane 1,3,5 triene. So hydrogenation is basically just adding hydrogen to something. So if we hydrogenate cyclohexene, okay, it has an enthalpy change of minus 120 kilojoules per mole. So basically cyclohexene has one double bond. So we're looking at, right, how much energy does it take to add a hydrogen molecule or hydrogen to a double bond in a cyclic compound. And from practical experimentation, we see that the enthalpy change is minus 120 kilojoules per mole. So if benzene did have the 3 double bonds like Kekule thought we had, then surely we would expect the enthalpy of hydrogenation to be 3 times that. So it'd be 3 times 120, which is minus 360. That's what we would expect if it had 3 double bonds. However, when we measure the enthalpy change hydrogenation of benzene, we actually get a value that's much lower, which is minus 208 kilojoules per mole. And this is the experimental value that we've actually calculated when working out with benzene, when we're actually adding hydrogen to benzene. So we can see here that predicted, if it had the 3 alternating double bonds, we would expect it to be minus 360 kilojoules per mole, but actually it's minus 208 kilojoules per mole. So what that means is effectively benzene is more stable. It's more energy is required to break the bonds in benzene than it is in cyclohexane 1,3,5 triene. So that means that benzene is a more stable molecule because we need energy. Energy is needed to break them bonds, and energy is so more energy is required to break the bonds, and energy is released when we actually form them. So if it's got a lower enthalpy value, it means it's more stable. So it's more stable. And the stability is due to that delocalized electrons. So that electron system within the benzene ring actually increases the stability, and therefore it is. You'll see later it's actually quite difficult to undergo reactions with benzene for this reason. So let's have a look at arenes. Now, arenes are is another word to describe a substance with a benzene ring in it. And benzene, obviously, on its own is fine. We've seen it there. But actually, we can add groups onto a benzene ring. And this is vitally important because it is in loads of pharmaceuticals use arenes in there. So we can name them in a particular way. So here we go. Here's one here as an example. And we'll come on to these. We'll see the reactions of these later on. But it's just to get the nomenclature bit out of the way. So what we do is, in these examples, we have benzene at the end. So, for example, bromobenzene, 1,2-dimethylbenzene. Now, the numbering of benzene rings, you just pick any number. Because it's a circle, we don't really need to know exactly where carbon 1 is or 2. We just assume it's 1, 2. So you always pick the lowest number. And just like you would do with any other molecule, we number it in the lowest way. So that's 1, 2. And then once you've labelled, obviously, 1, and you found where 1 is, then the other one, if there was 1 here, that would be 4, and that would be 5, and that would be 6, etc. And then nitrobenzene is another one. Now, sometimes you can have ones named as phenyl groups. So Here we've got phenol, and we'll look at phenol later on in a little bit more detail. Phenol is basically just a benzene ring with a OH group on the end, but we call it phenol for some reason. So we call it phenol, but for example, you might see molecules such as phenylamine, which has an amine group attached to a benzene ring, but we call that phenylamine. So just be familiar with the naming of them. Sometimes it'll be nitrobenzene, bromobenzene, for example, and sometimes it'll be amine at the end. But luckily, there's a limited number of molecules that you need to know, and a good start would be the ones that you see right in front of you there that you need to remember. Okay, so let's look at, because we've looked at benzene, and benzene has double bonds. What we need to try and do is look at the different types of reactions, how benzene reacts. But what we're going to do first is look at normally how do reactions happen with double bonds. Okay, and one of the classic examples is adding bromine to an alkene. So alkenes have a double bond, and they undergo something called electrophilic addition. Okay, so if we add bromine water to an alkene, it causes a colour change from a browny orange to a colourless solution. Now, you might have done this practical actually, where you've done a test for an alkene or a test for a double bond, and that's where you add bromine water to it and it decolorizes bromine water. So you might have done that already. You might have seen that. But basically, the bromine is the electrophile. Okay, so remember what an electrophile is. And you might have done this from you certainly will have done it in year one. So if you're not sure, go and have a look back. I've got videos on in the year one playlist, OCR year one playlist. Have a look back there to see what an electrophile is. But an electrophile is an electron-loving species. So it's a species which will attack something with a high electron density, such as a double bond. And what the bromine does is it adds on to the alkene. So you can see here, bromine's polarized. So what happens is we have a polarized molecule. So it's an induced polar molecule. As it approaches this double bond, we get electrons in this bond moving to one side of the molecule because of electron repulsion. So there's loads of electrons in that double bond there. And so what happens is the electrons move to the left-hand side and they bunch up onto the bromine. So we get repulsion. Now, the electron pair in the double bond is actually attracted to the delta positive bromine molecule, so the bromine atom, on the molecule there. And what happens? This breaks that bromine bond. So here it is. So the electrons, remember the curly arrows, always show the direction of electron transfer. So the electrons are in that double bond and they're moving towards that bromine, that delta positive bromine. Make sure you're drawing arrows correctly. Again, look back at year one notes, look back at the year one videos on an introduction to mechanisms, because that's very important that you need to know how a mechanism works. But it's moving from that double bond into the bromine there, and then what effect that is going to have is going to break that bromine-bromine bond. So we're going to form an intermediate, and this is a carbocation intermediate. So you can see our bromine has been added onto here. So the double bond is now broken. The bromine's added on, but we have a carbon with a positive charge, so it's a carbocation. We have a Br minus, because it was this bit here, this was broken off. We have a Br minus ion that's moving around freely. Now, that is effectively going to react with this. So what we're going to have is an arrow going from the lone pair to the positive charge on that carbon, and it's going to try and form a bond with that carbon. So here we go. There it is. So we're going to form a colourless compound, which is 1,2-dibromoethane is formed. So effectively, we've broken that double bond and we've added bromine to it. So that's the basic mechanism. So it's electrophilic addition, because the bromine is the electrophile and we're adding it to a double bond. Okay, so these are the standard reaction mechanisms for anything with an alkene, so anything with a double bond. Now, arenes undergo a very different type of reaction. Although we've seen there they could have double bonds, the double bonds, the electrons that would form double bonds, actually delocalize into a ring, and that completely changes the type of reactions that you can do with benzene. And actually they undergo electrophilic substitution. So this is why it's important to show you what a reaction is with an alkene and contrast that with what a benzene reaction would, what benzene reactions typically are. So benzene has a really high electron density in that delocalized ring. There is loads of electrons in there. So this is attractive to electrophiles. So these are electron-loving substances. Okay, so that's the key thing. So as we've seen, benzene is really stable. So remember that from what I mentioned before. So unlike traditional alkenes, as we've seen before, they do not undergo electrophilic addition reactions. And because what will happen is this will disrupt the stable ring of electrons. And one of the things that we know from chemistry is atoms are incredibly lazy. They don't want to be put in a position where they're less stable, if possible, unless they're forced to. So they don't undergo addition for that reason. So what they do is they undergo substitution reactions instead, and this is where a hydrogen, one of the hydrogens on the benzene, is replaced for another functional group, and this functional group would be the electrophile that we're reacting it with. And there's two mechanisms that we need to know for OCR. One is Friedel-Crafts Acylation, and the other one is a nitration reaction. So we need to know both of these and how they react. So let's have a look at the first one, which is Friedel-Crafts Acylation. So benzene is a massively, as I said right at the start, benzene is a massively useful chemical. It is used in pharmaceuticals. It's used in dyestuffs. It's used in pesticides, for example, herbicides. So it can be used in various different forms, and it is, without it we wouldn't have the things that we do have today. But due to its stability, benzene is really difficult to react. It's not the best molecule if you want a do reaction. Ideally, you want really reactive substances. But Friedel-Crafts Acylation can help solve this problem. So it was left down to these two chaps here, which is Charles Friedel and James Kraft. So Friedel was French and James Kraft was American. And what they did is they came up with a reaction where an acyl group, okay, which is this bit, RCO, is added onto a benzene molecule. And after that's added, the benzene structure is weaker and it makes it a lot easier to modify it. So once you've broken into that first, once you've substituted your first hydrogen, the rest of the benzene ring is much more susceptible to attack from other species. So it's actually a really, really important reaction. So in order to get onto the benzene ring, the electrophile must have a very, very strong positive charge. It's no good just having a delta positive, like we've seen with the bromine molecule. We must have a really strong positive charge here, because if we're going to attack this ring, we need something that is really, really powerful. Okay. Now, acyl groups have a positive charge already because they have that delta negative, delta positive interaction with the carbon and the oxygen. However, it's nowhere near positive enough. So what we use a halogen carrier, and this acts as a catalyst, and this will allow us to produce a much stronger electrophile with a much bigger positive charge, and that is powerful enough to break that barrier of substituting your hydrogen with your functional group. Okay, so in the Friedel-Crafts acylation, we react an acyl chloride with a halogen carrier, which is AlCl3, and we create a strongly positive electrophile. So let's have a look and see how this works practically. So to make this, we have to use aluminium chloride, so AlCl3, which is your halogen carrier, and we basically do this first. So our AlCl3 accepts an electron away from the acyl group. Okay, so here's our acyl group here on the left. So this is here, so this is our acid chloride, or acyl chloride, and then we have AlCl3, which is our halogen carrier. So what happens is we get the polarization. So as a result, the polarization increases and a carbocation is informed. So what happens is the chlorine on here now moves on to the AlCl4, and we now have a carbon which is heavily deficient in electrons, and it actually has a positive charge. It's not just a delta positive, it is a fully blown positive charge. It's a carbocation. Now that is a lot more powerful, and that means it will be able to react with benzene quite readily. So that's the first step. Before we do anything with benzene, we have to make our very powerful electrophile, and this is how we do it. And this is how the halogen carrier, hence the word halogen carrier, what it's doing is it's carrying the halogen from your acid chloride, and it's this that's then going to react with the benzene, because that's now got this really good positive charge. So we've made that electrophile. We need to now react it with benzene to make our stable phenyl ketone. To make a less stable phenyl ketone under reflux and a dry ether solvent. So the phenyl ketone is what we're making here. Okay, so here it is. Here's our benzene molecule, and we've got our carbocation there, which is our electrophile at the start. So the mechanism goes like this. So we have a delocalized electrons in that benzene ring are now actually attracted towards this carbocation because it's exactly what benzene is going to react with here because it's powerful enough. So the two electrons move from the bond, and that breaks the ring structure, and a positive charge develops. So you can see here what we've done is we've added our acyl group here onto the acyl group here. You've added it onto your benzene ring, and the hydrogen's still there. But notice we have a positive charge. Now, when you're drawing these mechanisms, you've got to make sure that you include your positive charge there. It's very important. And also, if you notice that the actual benzene ring has actually been disturbed, and it cannot extend beyond this carbon and this carbon. So it can't extend beyond the adjacent carbons to where the reaction has happened. Very important. So you've got to be really meticulous here. So this is our reaction here. So here's our intermediate that we formed, and remember we also have our halogen carrier that we formed before. Okay, remember that was from the previous reaction. So what happens is the negative AlCl4 minus is then attracted to the positively charged ring. Okay, because now you've got an opposite charge here, and one of the chlorine atoms breaks away to form a bond with the hydrogen. Okay, so you can see here, so we formed that bond. And then what happens is the electrons in the CH bond here then move back into that benzene ring there to neutralize that, and we actually reform our ring again. But our hydrogen has now left, and our hydrogen is left for the chlorine. So there's chlorine there, so there's HCl plus AlCl3. So we've reformed our halogen carrier back, and that is why we call it a catalyst, because the catalyst is never used up, it is reformed in the end. So you can see it's called a halogen carrier because effectively what it's doing is it's just carrying the halogen until this process here, until this step, when actually the halogen is used to make HCl. Okay, so let's look at our other type of reaction, which is the nitration of benzene. So nitrating benzene is useful. It allows us to make dyes and explosives. So, for example, TNT is trinitrotoluene. And dyes, you can make azo dyes with that as well. So don't worry too much about the azo dye bit, but we do use this. There is a use for this. So what we do is if we heat benzene with concentrated nitric acid and sulfuric acid, we form nitrobenzene. However, just like before, we have to make a powerful electrophile first. It's no good. We can't just take nitric acid and add it to a benzene. We have to make a powerful electrophile first. So here's the first step. So we make the electrophile, we react sulfuric acid with nitric acid, okay? Both of these are concentrated, so they're quite powerful acids. And so what happens is we form H2NO3+, so effectively this receives a proton, and this donates, so this loses a proton, so it donates the proton to form HSO4. Now, you would have seen in the previous videos looking at acids, bases, and buffers. If you have a look at that video, then you'll notice that actually, even though both of these are acids, this is a proton acceptor. So the nitric acid is a base. The sulfuric acid is actually acting as an acid because it is donating a proton. So it's funny because nitric acid, even though it's got the word acid in, it's acting as a base in this reaction. So you've got to, as long as you know that, because that's the Bronsted-Lowry theory. So then what happens is that H2NO3+ decomposes to form the electrophile of the nitronium ion, which is NO2+. So we've got H2NO3, which is here. That decomposes to form NO2+ plus H2O. And there, you can see there, we have, finally, our really powerful electrophile. That's what we want to add onto our benzene ring, and it has our positive charge there. Okay, so let's look at the mechanism for this. So we're going to use that nitronium ion that we've formed there, which is the NO2+, and we're going to react that with benzene to produce nitrobenzene. the mechanism is the same, and you'll see here, apart from the halogen carrier, the mechanism is the same. So let's have a look at the first bit. So the nitronium ion is attacked by the benzene ring, and that forms this positively charged ring, which is this bit here. And you can see we've added our NO2, and there's our positive ring structure. So the next thing is the electrons in the CH bond here. These move to reform the delocalized electron ring. So you can see there it reforms that back. And then what you have is your nitrobenzene that's formed, and H plus ion is formed as well back. Now, that H plus ion actually reacts with the HSO4 minus formed in the previous slides. Remember, in the previous one we had HSO4 minus left, and that forms H2SO4 back again. So actually, in this reaction, H2SO4 is a catalyst. So because it's reformed back again. So all these different points here, obviously you need to be able to write the mechanism down and show what's happening, but also you need to identify what's a catalyst and explain why it's a catalyst using your reaction mechanisms. So tie it all in because it all fits together. There's no loose atoms here. So this must be done at a temperature below 55 degrees Celsius, and this means you get a single nitration reaction here, right? Nitration substitution. If it's done above that, you'll get multiple nitration reactions. So you'll get NO2 on carbon 3, on carbon 5 as well. So you'll just keep nitrating it. So you've got to it's temperature sensitive. You've got to make sure it's done right. Okay, so let's look at phenols. When we looked at phenols, well, we introduced to it briefly just before as part of the nomenclature side. But phenols have a hydroxyl group, so it's an OH group, and that's attached to a benzene ring. So phenol, remember, is a benzene ring with the OH group attached at the top there. But we can also get things like 2-methyl phenol. So, for example, we've got a methyl group attached to the phenol, and the carbon with the OH group is always carbon 1 in phenols. Okay, so that's always carbon 1, and so then we go and name it 2. Now, if it was there, it would still be 2, because it'd still be called 2 because we always number with the lowest numbering system. So that's the IUPAC way. And this one's salicylic acid, and you'll see salicylic acid. You may see that as well later on, or in your practicals. Salicylic acid is used to make aspirin, which you may have made. So it depends if your teacher or your lecturer allows you to do that. Okay, so phenols are much more reactive than benzene due to their electron density being in the ring being higher. Okay, so what we've got is the actual OH group is donating some of the electrons or pushing some of the electrons it has into that benzene ring. So electrophilic substitutions are much more likely to occur with phenol than with benzene, okay, because of this this orbital overlap that we've been talking about. So the electrons in the p orbital of the oxygen, so that's the green one here, overlaps into the delocalized ring structure that we can see there. And so what this does is this increases the electron density in phenols and, like I say, makes them more reactive. So that means they're much more susceptible to attack from electrophiles. And this is quite important because what we're doing is comparing and contrasting reactions of benzene with phenol. And phenol has far more successful reactions because of this. So the position of the functional groups in a benzene ring can affect reactivity with electrophiles as well. So, for example, benzene has carbons that have the same electron density, so the reactivity is identical for each carbon. So there's no difference there in benzene. Substituted benzene rings distort the electron density, and it distorts the electron density in the ring, and so it affects the reactivity of carbon atoms in the ring as well. So just like with phenol, like we've seen before, that distorts the electron movement in the ring. So do other groups as well. So let's look at some electron withdrawing groups. So electron withdrawing groups affect substitution reactions on carbons 3 and 5. Okay, so electronegative groups such as nitrates, for example, as you've just seen before, this withdraws electron density from the ring, and specifically it withdraws it from carbons 2, 4, and 6. Okay, so you've got to remember that. And so this means your electrophiles are much more likely to attack at carbons 3 and 5. And so therefore, with nitration reactions, you're more likely to get reactions at carbons 3 and 5 than any other carbon because of the electron withdrawal nature of it. So let's look at electron donating groups. So donating groups affect substitution reactions on carbons 2, 4, and 6. But electron donating groups such as NH2 and OH donates electrons and increases the density of the ring, specifically at carbons 2, 4, and 6, as we labelled on that diagram. And so therefore the electrophiles are more likely to attack on carbons 2, 4, and 6, and so therefore substitution is more likely to happen at these positions. So this is things like, for example, phenol reactions, or phenylamine, as is shown in that diagram there. So let's look at an example of these different types of reactions. So let's predict the reaction between phenol and chloroethane, which is CH3CH2Cl, using an AlCl3 as a catalyst. So as the OH is an electron donating group, it pushes electrons into that benzene ring structure, that delocalized structure, then we're more likely to get substitution at carbons 2, 4, and 6. Now let's look at a second example. So predict the reaction between nitrobenzene and chloroethane. So here we've got a different type of phenyl arene compound. We've got nitrobenzene. And we've got chloroethane, which is the same substance. So this time we've got an electron withdrawing group, and so therefore we're likely to get substitution at carbons 3 and 5 instead. So there's a stark difference, as you can see. It really does depend on what type of group, what type of reaction, whether it's going to be a phenol or whether it's going to be, say, a nitro compound. Okay, so let's go back into phenols in particular. And phenols partially dissociate, which means they're actually weak acids. So you can see here we've got phenol, and it's partially dissociating, losing its H+. So remember, for something to be an acid, a Bronsted Lowry acid, it loses its proton, and therefore that's classed as an acid. But if it's a weak acid, it means that equilibrium lies well over to the left. So you're going to get, it's not going to dissociate fully, so you're going to get a lot of this and not much of this. So phenols react with alkalis to form salt and water. Because they're an acid, they react in the same way as acid-base reactions. So this is going to form salt and water. So in this case, we're going to form sodium phenoxide. Okay, so exactly the same as what you do with a standard acid-base reaction, and we form water as well. So there's no difference there. It looks a little bit different because it's got a benzene ring stuck on it, but it's a similar type of reaction. Okay, so phenols can also react with bromine water as well. So phenols react with bromine water, as phenols are much more reactive than benzene, remember, because of that ability to donate some of its electrons into that delocalized ring. And so what we observe is decolorization of bromine water. So you can see here, OH is an electron donating group, as we've said, so it pushes electrons into that benzene ring. So the reactions are more likely to happen at 2, 4, and 6. So we end up with a compound which is 2,4,6-tribromophenol, which we can see here. And also, obviously, we also produce 3-HBr as well. But we've decolorized it because we've gone from a brown bromine to a decolorized tri-substituted phenol. It smells of antiseptic. It's got this, if you've ever had a TCP before, which is trichlorophenol, instead of using bromine, we use chlorine. Then you'll know what it smells like. It's got that antiseptic smell, but so it's very similar to that, and it is insoluble in water, so it's quite oily. Okay, so phenols can also react with dilute nitric acid, and what they do is they produce nitrophenols, because phenols are much more reactive than benzene. So remember, when we tried to nitrate a benzene, we had to create a very strong, powerful electrophile. With phenols, we don't need to because they're much more reactive. The OH is electron donating, so we get substitution at carbons 2 and 4. So you can see here that we either get 2-nitrophenol or 4-nitrophenol. So this is the type of reactions that we get when we react phenol with dilute nitric acid. Okay, so these are the two isomers that we can produce. Okay, and that's it. So that's everything on aromatic compounds. So it's quite a nice topic. I quite like aromatic compounds. Please subscribe to the channel and show your support for the channel. That'll be great. Like I say, if you want a copy of these slides, click on the link in the comments box and you can get hold of them there. That'll be great. Yeah, I hope you found that helpful, and I hope it will help you to understand the difference, particularly between benzene and phenol, and why benzene is actually so stable and a little bit different. Okay, that's it. Bye bye.